Good afternoon. We're Team 43. Our project is predicting chaos using machine learning. My name is Matthew Flower.
I'm Danielle Williams.
I'm not no Burhay.
And I'm Rachel Arkins.
So our project explores chaos theory and uses a data-driven approach to model chaotic systems and ultimately to predict critical transitions. So a little background on chaos theory. It was discovered by a meteorologist called Edward Lorenz. He discovered a class of dynamical systems that are highly sensitive to initial conditions and diverge drastically based on changes in initial conditions. Um, Chaotic systems appear random and disorderly, but they are in fact deterministic and have an underlying structure. So we can classify real-world chaotic systems into two categories, ideal and non-ideal. Ideal systems are usually in controlled environments and can be defined using closed equations. Non-ideal systems would be much more difficult to define, if not impossible. And one possible way of modeling non-ideal systems is to use a data-driven approach.
So here's our data-driven approach. We use the time series data produced by the chaotic systems to train the neural network. And so the network implicitly learns the hidden structure of the system's dynamics, which means it can capture how the system behaves, even if it doesn't have the governing differential equations. And this is called reservoir computing. Reservoir computing benefits meteorological agencies and climate research centers as it's been shown to accurately predict atmospheric dynamics. It also benefits power grid operators in that it can predict voltage collapse prior to that occurrence. And ecological systems, it forecasts directly population dynamics and food chains, which matters for conservation efforts in ecosystem management. And in healthcare, it's been shown to show promise in the detection of atrial fibrillation just by data gathered from blood pressure waves alone.
We started by selecting four well-known chaotic equations, the Lorenz-Aizawa food chain and Hastings-Powell, and generating both the time series and a tractor in Python and MATLAB to serve as our ground truths. We then ran that data through our predictive model and evaluated the short and long-term predictive capabilities. In the short term, we see that the prediction is near exact, but as time goes on, the phase states diverge. However, the model still predicts the emerging dynamics and the shape of the attractor is preserved. We were able to improve our predictive capabilities by undergoing hyperparameter optimization, which had a significant impact, as seen in the figure. And finally, we added an injection channel into our reservoir so that the system can predict across multiple parameter regimes. This is what allows us to anticipate when the system is approaching collapse. Finally, you can see our results, and this shows that around step 2000, the real system did collapse into periodicity, and that our predictive model was able to capture this while still preserving the shape of the attractor.
For the future goals, we just want to take this and try it on real world stuff like weather or power systems. We also want to get better at predicting over a long period of time, especially near those points where the system can suddenly change. We also want to make it good overall since the real data is usually noisy, and we also want to make sure it's scaling up and make it more practical. So overall, we made sure that the reservoir computing is working really well for the chaotic systems. It was able to capture both the chaotic behaviors and when the system collapses, tuning the parameters, which helped a lot, and the model wasn't just memorizing, it was actually learning the system, which is a solid approach for predicting chaotic systems.